So we're going to develop, what we're going to do right now is we're going to develop a set of equations that allow us to solve all kinds of problems that involve constant acceleration. If you've got a time interval where the acceleration is not changing over that time interval, you can use these equations to help you solve the problem. Now, of course, we have let's start off with the definition of acceleration. It's the rate at which velocity is changing. So we say, delta v over delta t. Well, let's say that t is, we'll start at t equals 0. Our time interval will start at 0. And so if we have acceleration then is equal to, well, this will be my final. Delta v is final velocity minus initial velocity. And then we'll have that divided by time. Okay? And so what I'm going to do now is just take this equation, which just comes from the definition of acceleration, and I'm going to solve it for the final velocity. So let's multiply both sides by t. So I get a times t is equal to v minus v naught. And then I'm just going to add v naught to both sides. And I get v is equal to v naught plus at. So this is the first of what I'm going to call the kinematic equations. Now, this equation should look familiar to you because it's really just the equation of a straight line, right? If I graph velocity as a function of time, right? Well, here's my v naught. It's like my y-intercept. And then my acceleration is constant. Well, acceleration is the slope of the velocity versus time graph. So this is going to be a straight line. And if you have a straight line, you say, well, y equals mx plus b, right? That's the equation for a straight line. Well, look at this, though. Y. Well, what's the y-axis here? Well, it's not the y-axis, it's the, v-axis. And what's the slope? Well, that's delta v over delta t, right? The slope is the rise over the run. But delta v over delta t, the rise over the run, that's just what we called acceleration times time. I mean, this isn't the x-axis anymore. The horizontal axis is the t-axis. So here's my slope. X, we're now calling t, plus, now this is my value for y when x was 0. Well, this is going to be my velocity for v when t is equal to 0, or my initial velocity. And look, it's the same equation over here. Okay? Make sense so far? All right. So this is one of the kinematic equations. Now what we're going to do is I'm going to develop another kinematic equation based on area underneath the graph. Remember, recall that we've said that if your velocity, if you have a velocity versus time graph, the area underneath that graph, here's the area underneath this graph, that represents displacement, or how much I change my position. The area underneath a velocity versus time graph is displacement. Okay? Now, what shape is this? It's a shape with 4 sides, but 2 of the sides are parallel and 2 of the sides are not parallel. It's what is it called? It's a trapezoid, yeah. Now, it's a trapezoid that we can turn like this. Usually you think of trapezoids as like this is the base, this is one of the bases, and this is the other base. It's just a trapezoid turned on its side. So what we're going to do is we're going to call this the base and this the base. Well, here's v naught and here's v. So the displacement, the area of this trapezoid is the average base times the height. Do you remember that? The average base. Well, the average base, the base here are the velocities. So it's going to be the initial velocity, and up here is the final velocity divided by 2. times the height. Well, what is the height of this trapezoid if I turn it like this? You know, what's the height? Here's the base. It's time. Yeah, it's t. So just by looking at the area underneath the graph, I get the area of a trapezoid, but that represents my displacement. If the velocity. Now this is only a trapezoid if the acceleration is constant, because if this is not a straight line, you don't have a trapezoid anymore. Right? Another way of looking at this, by the way, what is v naught plus v divided by 2? It's the average of these two velocities. Well, here's the initial velocity, and over here, here's the final velocity. Well, v plus v naught divided by 2 is right in between them. So this is kind of the average velocity. Well, look, if I go across like this, notice that I could cut this triangle out and fit it in here and just have a rectangle. Anyway, that's another way of looking at it. So this is another one of my kinematic equations. Now the word kinematic means the study of motion. You know, kinematic means just motion. We're describing the motion of objects. Okay, so we got velocity, initial is equal to initial velocity plus acceleration times time. Here we have the displacement is equal to v naught plus v divided by 2. That's the average velocity times time. Now, what we're going to do is just play a couple of algebra games. And then you're also going to see the connection to this graph. And let me erase this. So I don't want to use that. Okay. What I'm going to do is I'm going to substitute for the final velocity in here. So I'm going to say delta x is equal to v naught plus v, right? Plus v. But what is v equal to? V naught plus at. So all I did was a substitution times time. Now all I'm going to do is clean this up. I'm going to, so you can help me do this. This is, what's v naught plus v naught? That would be 2 v naughts plus at divided by 2 times time. Then I'm going to just divide everything by 2, and I'm going to distribute this t in. So delta x will equal 2 v naught divided by 2, well that's just v naught, plus 1/2 at times t. So all I did was break that up. And now I'm just going to distribute this t in here. I get v naught t plus 1/2 a t squared. And this right here is one of my kinematic equations. Now I'm going to do another substitution. It's just an algebra game. Oh, one thing. Look at this one. V naught times t. V naught times t is really the area of this rectangle that I'm shading in right here. V naught times t is, right? Now this 1/2 at squared, that's the area of the triangle. Okay, so, hey guys, I'm recording over here, so please be quiet. All right, now, thank you. Now what I'm going to do is I'm going to take this, I'm going to solve it for time, and I'm going to substitute it in here. So we have v equals v naught plus at. So let's solve it for time. So time is equal to, well, it's going to be v minus v naught divided by a. So I did all that in one step. Here's t. First I got to subtract, then I divide both sides by a to get this. Now what I'm going to do is I'm going to take this and substitute it in here. And I'm going to get a new equation, and it'll be the last one. Delta x equals v naught plus v over 2 times time, but now time is v minus v naught over a. Okay? And so now I'm just going to play some algebra games here. Remember FOIL? This is v naught times v, and this is minus v naught squared. This is going to be plus v squared minus v naught. So I just multiplied, divided by 2a. Okay? You see what I did algebraically there? Okay. Now it's just a matter of cleaning up. Do you see anything here that's going to go away? There is something that goes away here. V naught, v minus v naught. See how they're the same thing? But this one is being subtracted. So this disappears. So, and now I've got this, so I'm going to say, well, delta x is equal to v squared minus v naught squared over 2a. Okay, so there's my equation. Now I could quit here, but for reasons that aren't all that clear to me, we solved this equation for the final velocity squared. So I'm just going to leave it to you. You can trust me on the algebra here. This is equal to, if I solve this for v squared, well, multiply by both sides by 2a and then add v naught squared to both sides. And I get v squared is equal to v naught squared plus 2a delta x. Now this is my fourth kinematic equation. Okay, so I've got 1, 2, 3, 4 kinematic equations here. All right. Now why did I go through all of this to develop these 4 equations? I'm going to show you something here that's really going to be helpful for your solving kinematic problems. I'm going to write the equations down over again. And I'm going to say, well, I've got equation 1. Where final v equals v naught plus at. Here, delta x is equal to v plus v naught over 2 times. That's the second one I developed, right? Now the third one I developed was delta x equals v naught t plus 1/2 a t squared, right? And then here is the fourth kinematic equation where v squared equals v naught squared plus 2a delta x. Okay? So these are our 4 equations. Now why did I develop them? Well, I'm going to make a little table here, and you can use this table on your equation list to help you solve problems. Now, what quantity is in equation 2, 3, and 4, but it's missing from equation 1? What quantity is in all of these, but it's missing from this one? This one it's missing from this one. It's delta x. See how there's no delta x in that equation? So it's no. Yes, yes, yes. What equation is missing from this? Acceleration. Yes, no, yes, yes. Which equation is missing from the third equation? I mean, what quantity is missing from the third equation? It's in all the others. The final velocity. Yes, yes, no, yes. And what's missing from here? Time. Yes, 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 no. So what this little table does is it gives me a toolbox, really. Here are the equations that I can use to solve problems. Now, what's in every single equation? Your starting velocity. You always have to know your starting velocity. Or you have to know everything else so you can solve for it in one of these equations. All right, now let's come up with a problem where you can use these equations, and I'll show you how to set one up. A poorly tuned Yugo. Now, by the way, this is really old-fashioned. A Yugo was a car made in the 1970s in Yugoslavia. It was probably the worst car ever made, but they did sell it. But it was super cheap, so there you go. Can accelerate from rest to a final velocity of 28 meters per second in 20 seconds. A, what is the acceleration? Am I still on camera? Yeah. Acceleration. And B, what is the displacement of a Yugo? Okay. Now I'm going to show you a problem-solving technique, and I think this is the first time that I went over this with my class. Given, find, and solve. Okay. So you write down given. Now what I like to do is draw a picture. So here's my picture. Here's my little Yugo, which really was a little pathetic car. And then I write down what's given around my picture, because that way I understand the problem better. So here it is at the beginning. So V naught equals 0, and then it accelerates forward until it's going over here. Whoops, changed shape a little bit. And its final velocity is 28 meters per second, and it did that after 20 seconds. All right, and so, and here's delta x right here. Now what are we trying to find? And notice that around my picture, I described what was given in terms of the variables that we use. V naught, t equals 20 seconds, v equals 28 meters per second. V naught, that's a fancy way of saying v sub 0, or v at time t equals 0, but I think it's a British thing. They used to say naught. Okay. So for part A, well, what do we want to find? We want to find the acceleration, A. For part B, we want to know delta x. So if this was a homework problem, if this is what was written in your book, you don't need to copy all of that. You can just use given, find, and then solve. Draw a little sketch, show what's given around your sketch, show what you're trying to find, and then you write solve. Now, let's do A. Well, I want to find the acceleration. Now, which equation up here on my table would be, it would be really stupid to use to try to find the acceleration? Yeah, you wouldn't. No, don't use this one, okay? But what you can do is use the other three. Now you have to kind of shop for an equation. Which one is going to fit what's given? Well, I know initial velocity, I know final velocity and time. And I want to find acceleration. So what's missing? Delta x. I don't know delta x, and I'm not trying to find it. So no delta x. Use equation 1. V equals V naught plus AT. And so now you can solve for the acceleration. Now, by the way, this is also delta V over delta T, so you can use that as well. It's 28 meters per second minus 0, right? The initial velocity was at rest. Yeah, look for that. Whenever it says at rest, that means it's 0. And t equals 0. I'm sorry, t equals 20 seconds. And then you get your calculator out. And so let's see. 28 divided by 20 equals 1.4. Meters per second every second, and that's my answer. Or you can put meters per second squared if you prefer. Now I'm running out of room here. I'll just squeeze it in here. What is part B? Well, you want to find delta x. Now look, you know everything. You know v naught, you know t, you know the final velocity, and now you know the acceleration, right? But wouldn't it be nice to not have to use the acceleration to calculate delta x? Because what if you made a mistake? Here, you're going to carry that mistake into the second part of the problem. So what I'm going to do is try to use the equation that doesn't have acceleration in it, which is the second one. And it's already solved. So delta x equals v plus v naught over 2 times time. So delta x equals v, which is 28 meters per second plus 0 meters per second divided by 2 times 20 seconds. Well, that's 10 times 28, 280 meters. So that's my answer for B. So you can use these equations here and this little table to solve just about any kinematics problem you're given. And it's a good skill to have. I mean, if you're working in business or you're an engineer or you're a doctor or something like that and you have equations that you need to use to calculate values, you need to know, okay, what do I know and what am I trying to find out and what relationships exist between those quantities here as equations, and then you can pick out the right one to use. And notice what I always do, by the way. I always write down the basic equation. I solve for the unknown. I plug in my numbers with units, and I show my answer with units. And I box my answers. That's what I'm going to expect you to do in all the problems like this. Do it just this way. Given with the sketch and the known values shown, what are you trying to find? And then you solve it. And if you, just a warning, if you try to skip steps, it's going to cost you more time. If your goal is to get the homework done, get the problems done in the least amount of time and get them right in the least amount of time, go through the whole process. You don't need to copy down the problem. So this part you don't need to copy down, but you do want to show your work properly. And it will help you not make mistakes. It'll help you get to the right answer very quickly. Okay? Very good.